That's the solution. It's an accomplishment to have such a solution. You can, if somebody gives you a value of the energy, you can calculate what is the phase shift. But we probably want to do more with it. So if you decide to plot this on a computer, again, there's lots of variables going on here. So you would want to figure out what are the right variables to plot this. And the right variables suggest themselves. From k squared equal 2me over h squared, unitless constants are things like ka, k prime a, and that's it. Well, so ka is a proxy for the energy, so ka squared is really 2me a squared over h bar squared. And this we could call anything. Well, let's call it u. On the other hand, k prime squared then, if you have k prime a squared, that is also unit free, would be 2me a squared over h squared plus 2m v naught a squared over h squared. And you probably recognize them. The first one is just u squared. I should call this u squared, sorry. U squared, and this is our friend z naught squared. It's that number that tells you the main thing you always want to know about a square well. The ratio between the energy V naught to the energy that you can build with H bar, M, and A. So here we go. We have K prime A given by this quantity, and therefore, let me manipulate this equation. Might as well do it. It's probably easier to consider just tan delta, which is the inverse of this. You would have 1 minus, the inverse of this would be k prime a over ka, put the a's always, so cot k prime a tan ka over tan ka plus k prime a ka cot k prime a. So in terms of our variables, k prime a is the square root of this. So k prime a is square root of u squared plus z naught squared. And k prime a over ka, you divide now by u. So it's square root of 1 plus z naught squared over u squared. That's this quantity. So, how much space do I need to write it? Probably I should write it here. 1 minus square root of 1 plus z naught squared over u squared. Cot k prime a is the square root of z naught squared plus u squared. And tan of ka, which is u, over tan u plus square root of 1 plus z naught over u squared cotangent of square root of z naught squared plus u squared. Okay, it's not terrible. That's tan delta. So if somebody gives you a potential, You calculate what Z naught is for this potential, you put Z naught there, and you plot as a function of U with Mathematica, and plotting as a function of U is plotting as a function of Ka, and that's perfectly nice thing to do, and it can be done with this expression. In this expression, you can also see what goes on when U goes to 0. Not immediately, it takes a little bit of thinking, but look at it. As U goes to 0, well, this number is a 1, that's perfectly okay. That seems to diverge, goes like 1 over U, but U going to 0, this goes to 0, so the product goes to a number. So the numerator goes to a number, some finite number. On the other hand, when U goes to 0, the denominator will go to infinity, because while this term goes to 0, the tan U, this number is finite, and here you have a 1 over U. So the denominator goes to infinity, and the numerator remains finite. So as U goes to 0, tangent of delta goes to 0. So you can choose delta to be 0 for 0 energy. So as U goes to 0, you get finite divided by infinity and goes to 0. So tan delta goes to 0, and we can take delta of Ka equals 0, which is U, to be 0. The phase shift is 0 for 0 energy. Let me go here. So here's an example. Z naught squared equals 3.4. That actually corresponds to 0.59 pi for Z naught. Z naught equals 0.59 pi. You may wonder why we do that, but let me tell you in a second. So here are a couple of plots that occur. So here is U equals Ka, and here's the phase shift, delta of U. You have the tangent of delta, but the phase shift can be calculated. And what you find is that, yes, it starts at 0, as we mentioned, and then it starts going down, but it stabilizes at minus pi, which is a neat number. That's what the phase shift does. The so-called scattering amplitude, where you could say, when is the scattering strongest? When do you get an extra wave that is propagating more strongly? So you must plot sine squared delta. And sine squared is highest for minus pi over 2. So this goes like this, up and decays as a function of U. Third thing, the delay. The delay is 1 over A the delay is 1 over A d delta dk as a function of U. So that, you can imagine that takes a bit of time, because you would have to find the derivative of delta with respect to U and do all kind of operations. Don't worry, you will have a bit of exercises on this to do it yourselves. But here the delay turns out to be negative, and this is unit free, and here comes to be equal to minus 4 for U equals 0 and goes down to 0. So in this case, the delay is negative, so the reflected packet comes earlier than you would have expected, which is possible because the reflected packet is going slowly here. Finally, at this point, reaches more kinetic energy, and then back. So that's the delay. And you can plot another thing, actually it's kind of interesting, is the quantity A, this coefficient here, that gives you an idea of how big the wave function is in the well. How much does it stick near the well? So it peaks to 1, and it actually goes like this, and this behavior of this form. Basically, it does those things. So far, so good. We got some information, and then you do a little experiment and try, for example, Z0 equals 5. And you have delta as a function of u, and here is minus pi minus 2 pi, and actually you find that it just goes down and approaches now minus 2 pi. So actually, if you increase this Z0 a bit, it still goes to pi, a pi excursion of the phase, but suddenly at some value it jumps and it now goes to 2 pi. And if you do with a larger value, at some point it goes to 3 pi and 4 pi, and it goes on like that. Well, if Z0 would have been smaller, like half of this, the phase would go down and would go back up, wouldn't go to minus pi. It does funny things. So what's really happening is that there is a relation between how much the phase moves and how many bound states this potential has. And you say, why in the world? This calculation had nothing to do with bound states. Why would the phase shift know about the bound states? Well, actually it does. And here is the thing. If you remember, you've actually solved this problem in homework, the half square well, in which you put an infinite wall here. And if you had the full square well from minus a to a, this problem has all the odd solutions of the full square well. All the odd solutions exist. And if you remember the plots that you would do in order to find the solutions, you have pi over 2, pi, 3 pi over 2, 2 pi. And here is the even solution, even. Here is the odd solution. I'll do it like that. Here is an even solution. Here is an odd solution. And I mark the odd solutions because we care about the odd ones, because that's what this potential has. So Z0 equals 0.59 pi is a little more than pi over 2, so it corresponds to one solution. So there is one bound state for this Z0. Z0 equals 5 is about here, is in between 3 pi over 2 of this, and there's two nodes, two intersections, therefore two solutions in the square well, and here we have that the phase has an excursion of not just pi for 1, but 2 pi. And if you did this experiment for a while, you would convince yourself there's a magic relation between how much the phase shift moves and how many bound states you have in this potential. This relation is called Levinson's theorem, and that's what we're going to prove in the last half an hour of this lecture.